but we'll go from the current slide. Here we go. Okay, can't think of anything too new. Appreciate getting a couple papers in this morning from both people who are here this morning, but the others will be coming. We are making decent progress on Chapter 2. It's a fairly long chapter, quite a bit to cover here, but I think it's going along. I just like it better than Chapter 1. And any questions on anything we've covered so far? All right. We're in Chapter 2, as I said, first-order differential equations, and 2.3 is covering linear equations. And by the way, Screencast-O-Matic is back up. You weren't here last time, right? But you were, right? Or were you? Yeah, okay. And Screencast-O-Matic would not come up. And I found out someone had failed to renew the site license. So they got it open sometime before 4 o'clock, because my 4 o'clock class, I tried it every class. 10 o'clock class wouldn't work, 12 o'clock class wouldn't work, but then on my 4 o'clock class, it did work. So they got it, the site license renewed before 4. But those first 3 classes, there's nothing out there from this class on YouTube. However, I'm going to leave what my best guess was the corresponding time I did it last, I believe it was last spring or sometime whenever I last taught this course. But you know there's a problem. In the spring, the classes were an hour and 15 minutes. These are an hour and 50 minutes. So there's no way it's going to wind up so that it's going to be exactly the same class. There may be some overlap or there may be some gaps. I'll try my best to guess well. Now, here's the other issue. If you've been to the playlist on YouTube, you'll see, I hope you've noticed that this class always loads at the bottom. So you have to go near the bottom of the playlist and find where we started. I don't erase last term because of the very thing that happened on Tuesday. The system failed, okay, and I couldn't record. So I'll leave all the classes out there, so in case I need to refer back to some of those, if I were to be absent and we have to miss a class, you could still follow approximately where it would be. So you'll need to go to the top of the playlist to get the class from last term, and the bottom of the playlist to get the ones from this term. So that's what we got. All right, if there's no questions, then let's move on to example 6, bottom of page 59. An initial value problem. Solve this. Okay? dy dx plus y is equal to f of x. Boy, that's not very specific, isn't it? And it's an initial value problem that y at 0 is equal to 0, but where f of x is a piecewise defined function. It's 1 anywhere the x is between 0 and 1, and it's 0 beyond that, x greater than 1. Okay. Now, the interesting thing is, this is not defined at all for negative x's.
Is this on 2.3?
This is 2.3, page 59, example 6, bottom of the page. Are you on the ebook or are you finding it?
Yeah.
Okay. All right. Rather bizarre function here. Okay? That's your f of x. Okay? Now, I think it's fairly obvious we can't use separable variables here. It's just not going to work, okay? Let's see. I guess, yeah, if you broke it into two domains and did one and then the other, yeah, you might be able to get it to work. But let's use the technique we are doing now, linear equations. What's our first step? Okay, you're trying to solve it almost by separation of variables. I don't think that's going to be a really good idea on this one. So let's do linear method. And in the linear method, that's what they call it. I think that's generally the term. Solving a linear first order equation. Remember, the first step is identify your P of x. That's the coefficient of y. What is that? 1. Okay, so here we have P of x is equal to 1. All right. Come off the right. Okay. All the X chromosomes are showing up. Where are the Y's? Huh? Okay. All right. And what do we do with that P of x? Once we found it. We integrate it. Okay. And what's that? X. Okay. Don't put any constants on it, just x. And what do we do with that x? That integral. Here's Rod. Okay. This is example 6, bottom of page 59. What do we do with that x, that integral of P of x? Sort of a strange little step. It's going to be a function that helps us do a product rule. And the function that best helps you do a product rule is the E function, because it's so easy to differentiate, right? So you raise this and do e to the integral P of x dx. So that in this case will be e to the x. All right. Well, what do you do with the e to the x? Multiply it by everything on both sides. So it'd be x dy dx. I'm sorry, e to the x dy dx plus e to the x y is equal to, now this time I think I will do it. Let's split this into two different differential equations. The first one is going to be with f of x equal 1, so that's just going to be 1, so that's going to be e to the x. Now this is going to be good for x's between 0 and 1, inclusive. The other differential equation would be if this is equal to 0, and that would be for all x's greater than 1. So we have two differential equations here. Let's deal with one of them, then we'll come back and do the other. Okay? Now, the thing to note here, remember we want this to be a product rule of the derivative, right? Let's see if it is. Okay? Is this a d by dx of some product? Well, the y has to be one part of it, and then the thing you just multiplied has to be the other part, e to the x. Now the question is this indeed true? Well, derivative of a product is the first times derivative of the second. That works. Plus the second times the derivative of the first. That works. So this is a perfect derivative, okay, of that product, okay? Now, the first thing we're going to do, I'm going to come up here and do it, and do d by dx of e to the xy is equal to e to the x. That's the top half. Okay? Well, now is the time to multiply by dx. This is d of e to the x y is equal to e to the x dx. Right? Follow? Make sense? Okay? Well, the integral, now we integrate both sides. The integral of a perfect derivative is e to the x y. It's whatever is inside that d symbol, okay? And over here, what's the integral of e to the x? Integral of e to the x dx. E to the x, okay? Now, and this is where we can put our plus c, okay? We need to put our plus c. But I'm going to write it as e to the c. That's also a constant, isn't it? I'm just choosing to write it differently, okay? Now, the next thing that we've got to do is isolate the y, okay? So we're going to divide this by e to the x, divide this by e to the x, divide this by e to the x, okay? Those go out, these go out, leaving 1. And here's Lauren. Okay? So we're just missing Curry and Jasmine. Okay? So, our answer, as indicated here, for this one would be y is equal to 1, and then let's write this as e plus e to the c minus x. Is that okay? That's why I wrote it as e to the c. When you're doing the division of two same bases, different powers, keep the base, subtract the powers. Right? So that's one way to express it. Actually, there is a slightly better way, now that I think about it. I shouldn't have done that. Left it as a c, because e to the c times e to the minus x, e to the c is just a constant. So I think a better way would be y is equal to is equal to 1 plus a different c here, c e to the minus x. I think that's the better way to write. And Curry decided to show up this morning. Good deal. Okay? So now we're just missing Jasmine. All right. So, we're doing example 6, bottom of page 59. We're probably on to the top of page 60 by now, but I haven't flipped over yet. Okay? So here is our solution for x is between, no, I wrote it down somewhere, here, right here, between 0 and 1, okay? But we have a boundary value, don't we? Y of 0 equals 0. So that means this function is limited to that part. Why even mess with the second part? Because that x is greater than 1. Yeah, there's a solution out there, but we can't find out what the c is, because the c is only good for this part of the f of x. Okay? So, let's evaluate and see what your c is. When you put in a 0 for x, you get 0, because y is 0 also, is equal to 1. Let's use this form, plus c, right? Because e to the 0 is 1. E to the minus 0 is 1. So this indicates that c is equal to negative 1. So our solution is y is equal to 1 plus e minus e, writing it this way, minus e to the, if I repeat myself, I'll write it again, okay? E to the minus x. Okay. Now, there are a bunch of solutions probably out where f of x equals 0, but we can't use our boundary condition on those, so those would still have a C on them. Now, do they do that and retain a C there? Yeah, they do. Okay, so let's do the second part. Let's do this part. I think you'll find that basically just as easy, maybe easier, because now you have this is equal to 0. Okay, whereas there it was equal to e to the x. Now it's just going to be equal to 0. Well, that would be, going to do the same procedure here. That would be d e to the xy is equal to 0 d by dx. Okay, and multiply both sides by dx. Okay, integrate. Now, don't let the 0 mess you up here. Think through it. Okay, this would be the perfect derivative e to the xy, and this will be what? Integral of 0 is what? First tendency would be to say 0. But think about it. Antiderivative of 0 is what? What, when you take a derivative of it, you'll get 0. A constant. So this is going to be some constant. They call it C2. Fine, they called the other one C1. We found out what C1 was. Okay? So divide both sides by e to the x, and you get y is equal to C2 e to the minus x. We can't evaluate the C2 with our initial condition. So it's this for any time x is between 0 and 1. It's that anytime x is greater than 1. Not defined for anything less than 0 at all. Okay? Now, an interesting thing to note here, okay, and this is just interesting to note, the y here, as x is increasing, now it can't increase much. It can't go past 1, because that's the only place x is defined for this part of the solution. But this would be 1 minus e. And e is 2.7 or something like this. So this is a slightly negative number. If your x were to continue to increase, then this is going to go to 0, and you have 1. And as x goes to 0 there, you would be heading for C. C2. No, I'm sorry. That would just be going to 0. So not really all that interesting. Except this is going to the 1 up there, and the other is going to 0, which is what your alpha x is. So, probably not important. Okay. So, okay. Now, here's the next issue. By appealing to the definition of continuity at a point, it is possible to determine what C2 is, so that the foregoing function is continuous at x equal 1. Now, nothing said it had to be, but it's sort of a nice thing to happen. If this was a real-life function, it almost has to be continuous, because real-life functions don't suddenly jump. You know, they don't suddenly go from one value to another value. They always have to have something in between. So, in other words, the pen can't jump off the page. It has to continue. So let's do what we need to, and of course, the key point is what's happening at x equal 1. And that's what I just was doing, kind of. When x is equal to 1, y of 1, this will be 1 minus e. No, 1 minus 1 over e. Sorry about that. I thought this shouldn't be a negative number. 1 over 1 over e, okay, which is about 1 minus a third, so this is something close to 2/3. I'm not going to write it down exactly, but it's something sort of close to 2/3. Not there, but close to it. Okay, but let's just leave it 1 minus 1 over e. Well, if we want that to be at 1 here, then using this one, y is equal to c2 e to the minus 1, and you want that to be 1 minus 1 over e. Well, let's write this as c2 over e is equal to 1 minus 1 over e. Multiply everything on both sides by e, and you get c2 is equal to e minus 1. So that's going to be, that should be a c sub 2, not a c squared. Don't know what the hands are doing this morning. C2. So in that case, for the second part of it, the y is equal to e minus 1 times e to the minus x. Now you might be able to clean that up a little bit and call it y is equal to e (1 minus x minus e to the minus x). I don't know if that's any cleaner, but so 1 minus, where is it? There it is. 1 minus e to the minus x for the first part, 0 to 1, and then e minus 1 times e to the minus x for the anything greater than 1. And that does give you a continuous function. Not differentiable at that boundary point, but continuous. Okay? That's a really messy slide. Let's see if I can get this somewhere in the middle here where you can see it. Here, of course, is the function 1 from 0 to 1, and then 0 elsewhere. That's your driving function. That's the f of x at the end. And when you do this and match them up so they're continuous there, this, the first one there is, this one right here, is a function going up like this. It gets almost to 2/3, or maybe just past 2/3, and then after that, it comes down to this one, okay? And that is then the graph of that. Not a very exciting looking graph, but it is the function that satisfies those conditions. Obviously, you have a discontinuity of your first derivative there, but that's what your original problems showed you. There was a discontinuity of the first derivative there, but discontinuity of the first derivative, but the function still continues. Okay. Now, they throw something else in here, which is largely for your information. And I know it's exciting information, so take advantage of it. Do I need to leave this up a little longer? Anyone need it? Got it? Okay. It's talking about the error function, okay? And yes, there is a function called the error function, okay? And here is how it's defined. Now, they say a little bit to begin with, so it's not all of you have your books. In mathematics, science, and engineering, some important functions are defined in terms of non-elementary integrals. In other words, integrals that you really can't evaluate analytically, okay? If you evaluate them at all, it's going to have to be basically numerically. Two special such functions are the error function and the complementary error function. And here is the error function. And it's given the name ERF. Error function of the variable x, and this is equal to 2 over the square root of pi, really bizarre coefficient in front, times the integral from 0 to x. This basically is going to the fundamental theorem of calculus part 2, basically. You define it as an integral, okay? E to the minus t squared. Now, t is just a dummy variable here. You can't use x because x is your limit variable, okay? dt. Now, it seems like we hit this a little earlier, and I suggested to you this is the function that basically, not quite this, but something that looks fairly similar to this, is the one that plots to be your bell curves, you know, and those kinds of things, and used in statistics a lot. Not exactly this form, but fairly close to it. And that kind of makes sense. That statistics deals with probabilities which are not certain. They would have error in them. But that's that's just a really wild grasp to make it make sense. Okay? Now, similarly, they mentioned the complementary error function, which is ERFC for complementary, also of the variable x, and it has exactly the same coefficient, 2 over square root of pi. Again, a really bizarre number. If you think about it, pi is an irrational number, and then the square root of pi has got to be a doubly irrational number. It's just irrational. But okay. Now, this one is the one that goes from x to infinity. Okay? And that's e to the minus t squared dt. Now, they look like they're, I mean, almost the same type thing. They follow this up with something that I'll get to in just a second. But you see, the first one is defined from 0 to any value x out here. You choose your x, any value, and then from there on, you get the rest of it, okay? Same function, same everything, it's just it's going from x to infinity, okay? Now, they make a little statement that I find somewhat obnoxious in the smugness of it, okay? It says, from the known result, yeah, for sure, that the integral from 0 to infinity of e to the minus t squared dt is equal to the square root of pi over 2. Of course we knew that, didn't we? Okay, now if you want to see a proof, go to Appendix A. They've got it back there in Appendix A. Okay? Now, from that result, here is what we get. You see that the sum of these two has got to be that. So the sum of, let's write it down here, 2 over root pi times the integral from 0 to x of e to the minus t squared dt plus the integral from x to infinity of e to the minus t squared dt. Almost seems like you're playing, and by the way, it has a 2 over root pi in front of it too. That has to be equal to this, the integral from 0 to infinity. That covers both of them, right? Okay? Well, we know the answer to that. That's root pi over 2. Okay? We know that the sum of those has to equal that. So, factor out a 2 over root pi from this. Okay, no, sorry, I didn't quite say that right. Should have factored out first. Sorry about that. Integral from 0 to x e to the minus t squared dt plus integral from x to infinity of e to the minus t squared dt. That has the equal, wait, this thing in here is what they told us is equal to this, and this is root pi over 2. And since you factor this out, this is equal to 1. Okay? So, the this entire thing here, this one, okay? The sum of these two is equal to 1. That's what we got. The sum of those two is equal to 1. All right. Hopefully, this is ringing and it's really faint in distance, a probability bell, okay? The probability of something being between 0 and x would be some probability. You can't get less than 0 and you can't, okay, right? So that's some probability. And then the probability of it being beyond x is the rest of it. And the total probability is 1. The probability that it is 1, okay? So this is very closely related to probability, okay? So that's probably way more than we needed to say about it. But just to introduce you so you've seen it, and example 7 is going to have you use it too, okay? So let's see what we can do with that. All right, to erase. So solve the initial value problem, dy dx minus 2xy is equal to 2 when you know that y of 0 is equal to 1. Okay? Where would you begin? Anybody? Okay, I don't think you're going to be able to do separable variables even if you work that up really hard. So let's not even try that route yet. But this is obviously set up to be a standard form for the linear equation. And what's your first step with the linear equation? Yeah, get it in standard form, and I think we got it, right? Okay, and then figure out what the P of X is. What is your P of X?
2x.
With a minus. Negative 2x. And what do you do with that P of X? What do you do with it? We integrate it with respect to x. Okay? And that integral gives you what? A little louder?
E to the negative 2x.
Okay. Say that one more time.
Do you do to E?
Say again?
To E? Do you integrate to E? Or
Okay, yeah, let's do the integral first. Integrate that integral. It's a pretty simple integral. What is it?
negative 2x?
Negative what? Negative x squared. Okay? If you've got any doubt, then take a derivative of it, you should get that. And sure enough, when you take the derivative of this, you get negative 2x. Yeah. So remember, when you're integrating a polynomial, take the variable, increase the exponent by 1. This is 1, so that moves it up to 2. Divide by that exponent. Dividing by 2 cancels out the negative, the 2, and so you have a negative x squared. So there's your integral. Don't ever put a constant with it, just the integral. Okay? Now, what do we do with that? And there's where you're jumping next. take the e of it. So e to the minus x squared. And then what do you do with that? Multiply it by everything on both sides. So that gives you e to the minus x squared dy dx minus 2xy e to the minus x squared is equal to 2e to the minus x squared. Okay? Now, what do we do here? I guess I'm overly cautious and don't trust that I've done everything right, but as a check, or a slow lock, no, okay. As a check, what I'm going to do is see if indeed this forms the derivative of a product. That's what it's supposed to. And what the product is always supposed to be is what our integrating factor was, e to the minus x squared times your y. That is what it's supposed to be. Let's see if we indeed have that. Okay? Let's take the derivative of this, and the first part's easy. It's derivative is the first times the derivative of the second. That's exactly what we got here. That part's good. Let's do the second part of your product rule. This, y, there it is, times the derivative of this. And what is the derivative of this? Derivative of e is an e to the minus x squared. But then you do the chain rule on the second part, on the innermost function, and that would be a minus 2x. Sure enough, that is a perfect derivative of that product. Okay? That's what it better be. Okay? Now, this is equal to 2e to the minus x squared. Okay? Now what we're going to do is write it in differential form, and the integral of this is simply e to the minus x squared y. And this is where we run into problems. This is 2 times the integral of e to the minus x squared dx. Okay? Now, this is an impossible integral to integrate, okay? But that's your error function, or something pretty close to it. If we put t's in here as a dummy variable and go 0 to x, that would be your error function, okay? And we know from the previous work that we did what that value for the error function is, okay? And so we'll rewrite this as 2 times the integral of from, I don't feel comfortable putting limits in there, but that's what they do. Okay, and they go 0 to x of e to the minus t squared dt. Okay, now they did it back earlier too, but I just don't see a reason for doing it on the other side. But let's go with this. Okay, now we know this from before is what? The error function. I've got to that if we multiplied that by, let's see, if that were a 2 over root pi, that would be the error function. So that would be pi times, or root pi, times the error function. I don't know if that's helpful to us, but that's what we've got here. So I guess I just leave it. Sorry. no reason to do that even. They just leave it alone, okay? They're not going to evaluate the error function. I thought maybe they'd have us look it up in a table, but they're not. So this is what we've got, all right? Well, let's carry it the next step. Multiply both sides of this equation by e to the x squared, okay? So we have y is equal to 2e to the x. Yuck. Because you're multiplying by that, 2e to the x squared times the integral of 0 to x e to the minus t squared dt. Okay. Okay. Now, actually, they left it in the first form. I can't see any particular reason to do that, but they did. I guess because of your constant. You aren't able to do a constant of integration here, but we do know that when when x is equal to 0, y is equal to 1. So let's plug this in and see what we get here. Okay, if we plug in x equals 0, y is equal to 1, we have 1 is equal to 2e, well, x is 0, that's just 1. Okay, so that'll just be 2 times the integral from 0 to 0, that is an x up there, of e to the 0, which is 1, and seems like to me that would be 0. Okay. Okay. E to the minus, okay, sorry. Nope. I just don't see how they get what they got. Okay, what they say is exactly what we have down here, this thing equal to that thing, okay? All right, that's exactly what we have. Oh, got it, maybe. Sorry about that. It's kind of some bizarre things they do. And frankly, I don't see a real benefit in going through this, but they didn't quite get that they have a y to x minus y to 0 there, because they integrated both sides with respect to t from 0 to t. And so, sorry, because they do this with respect to t, they also integrate this with respect to t, which is 0 to x, and you have to put a t in here, and this is a y of t, okay? Now, when you integrate that, because it is a perfect it's a product rule, that would give you, and this is where they introduce it, it's e to the minus x squared y of t minus e to the minus x squared y of 0. But of course, if you put 0 in for x, or t, or whatever, this would be a 0 here too, and e to the 0 is 1, so you get and that's how they get their constant, and y of 0 is 1, okay, and so then your y of t, you'll multiply both sides by e to the x, so your y of t is equal to e to the x squared times 1. So, plus, or minus, no, plus this thing here, okay? All right, you multiply both of them. So again, it's sort of going around your elbow to get to your ear, but you can get there. And you see from these equations that the error function, you can go back and express it in terms of error function, but guess what? You've got to use either a table or numerical approximation or something else to evaluate the error function. So you'd almost have to have a package to do it, so I don't think it's worth going into any more detail there. Let's do homework exercises. 2.3, and again, the answers to odd number, selected odd number problems are in the back of your book. Okay? So do any of the odds 1 through 23. Do any of the odds 25 through 35. Do either 37 or 39, or both if you choose. That's like the one we started out with today, where you have piecewise defined function. Then do 41. And you can work with 43 if you'd like. That's an error function problem, little bit involved and complicated, but if you want to follow it up, do that. Similar to the one we just did, and we didn't carry that all the way through, so if you want to do it, you can. Try 45. Now, and this sort of irritates me here too, but here they're introducing a couple of other functions. Problem 47 gives you the sine integral function, which is an integral you can't do in real life, okay? You can only approximate it or you do it numerically. And then 48 introduces the Fresnel sine integral, which is s of x, capital S of x, where the sine integral is si of x, okay? And you can play around with that. Well, 48 isn't in the back. Most of the time the discussion problems are not in the back of the book, but you're welcome to look at those if they'll give you any better, deeper insight. Now, your mathematical models probably aren't in the back either, but that may be something that would interest you. And by the way, the sine integral function, the Fresnel integral function, the reason I mentioned those is those are potential paper topics, like who developed this, how was it developed, why was it developed, what are applications of it. Any of those would be a potential paper topic. And another possibility would be radioactive decay series. Those are definitely used in many areas, medical and other areas, carbon dating, that kind of stuff. You can look at that. If, again, none of these answers are probably in the back, but a heart pacemaker, how is that related to differential equations? It is, okay? They very much a part of that. So that's the main reason I mentioned that, because I just want to remind you, you do have a paper for this course. And let's see, how many have I gotten in so far? Oh, 0. Okay. out of this class. So, in fact, this is really scary. In all the classes, I'm teaching 6 classes this summer. Now, one of them doesn't have to do a paper there, medical type stuff. But of the 5 classes that I consider a bit more academic, that's an academic course, only two papers have come in, and we're almost at midterm. So please, folks, don't forget to work on your papers. That's why I gave you several possibilities there. There's also listed there computer lab assignments. If you have a CAS, that's computer algebra system, or have access to it, and you want to look at it, you know, play away. Okay? Any questions? 2.3. This was the button I wanted to hit. All right. So let's move to what we call exact equations. Huh? The names for these are rather bizarre. A linear equation is a linear equation, yet there's a whole technique for doing linear equations if you get them in the standard form. Okay? Well, now we're dealing with exact equations, which, by the way, are also generally linear equations. All right, so here is where we begin. What if you had something that looked like this? Y dx plus x dy is equal to 0. Okay? Is that a differential equation? Yeah, it really is. I think what I would do would be subtract the y dx from both sides, and okay, and that would give me x dy is equal to minus y dx, and then this isn't fair, but divide by dx. Write it in different derivative form. That goes away, and you have x dy dx is equal to minus y, and then you can multiply both sides by x. Dy dx is equal to minus y over x. Okay? Now, or you didn't have to subtract it all. You could have written it this way from the original problem, rearrange the order, but dy dx plus y over x is equal to 0. That's dy dx plus 1 over x y is equal to 0. That's a good old linear equation, okay? That's ugly. All right. That's a good old linear equation. And, by the way, the way I did it first, we could make them separable equations. Multiply both sides by dx and divide by minus y. Yeah, you got a separation of variables. So, yeah, there's several ways to do this. Okay? And that is a differential equation, first order, meaning it is linear, and both separable and linear. Okay. However, even though that's doable, and probably doable pretty easily, we can solve the equation by an alternate manner. Yeah, we wanted some other way to do it, didn't we? By recognizing that the expressions on the left-hand side of the equality of that first thing is the differential of the function f of x, y equal. Okay, so let's go back. Forget all this other stuff that I was doing. Okay, go back to that first equation. Probably would have been easier to erase everything and just write it again, but let's see. This isn't going too slowly, so let's do it. Now, here's what they're suggesting. And it's true. Let's suppose that f of xy is equal to the function xy. Okay? So, let's do d by dx of xy. We're stuck on product rules, aren't we? Let's do that. What would you get? Actually, I hope you're okay with it if we just do it in differential form. Okay? So let's do it just in differential form. What would that be? Product rule? Second? Okay, not quite. X dy, right? First times the derivative of the second, plus y dx, right? And isn't that exactly what we got up here? So basically, this form that we have here is a exact derivative of a product of two functions, right? That's what that is. Exact derivative. So if you wanted to undo that, just integrate it. But that's the, oh yeah. Okay. So in this section, we're going to examine some first-order differential equations that are a lot more complicated than this. And here's what they're going to look like. M of xy dx, I'll make sure I name them the way they do, plus n of xy dy is equal to something. And they're all going to be, for now, they're going to be 0. Okay? Equal to 0. Now, that won't work for every function you can think of, m of xy and n of xy. But it will work for some. So, what the first order of business is, or they're going to tell us, is applying a simple test to these two coefficient functions to see if this is a differential of some f of xy. If the answer is yes, we can construct the f by partial integration. Okay? Now this sounds like it's going to get involved. And in a sense, it really is sort of involved, but then it really opens the door to solve some pretty complicated looking problems with repeatable steps. I think I've said it before, my calculus professor at Georgia Tech, when we finished, we were on the quarter system, 5 quarters of calculus. We finished that, I had him for all 5 quarters, which was totally bizarre. And it was almost the same, wasn't the same group of people, but it was the core group had carried through that. We had lost people along the way, but it was an interesting situation. And we finished a little early, I think about a week early. He said, well, since we got a week to go, let me introduce you to differential equations because that's what you're going to do next. And he would talk about things, and finally he said, so differential equation basically comes down to, if you can't figure out how to do it, try a trick. If the trick works more than once, call it a method. And that's almost what you're doing here. We're going to develop a trick that works, it seems like, every time, and we'll say, okay, this is the method we'll use. We just did that with the integrating factor. Look, find the p of x, integrate the p of x, raise that p of x, the integral of p of x to e to that power, then multiply everything by it, and lo and behold, that becomes a perfect derivative, okay? And then you can integrate it. Well, we're going to do almost, not the same thing, but we're going to do a similar procedure here to determine. So, how they start here, and they can really make things as complicated as possible. They say, let's say that this thing we just said here, only it's not the, okay, in fact, let me get this other stuff off because we're through with that. That function certainly works, but it's not the only one that does. I probably should have erased everything first. I meant to leave that though. All right. The f of xy we had, let's name that z. Z is equal to f of xy. Now, it's not that same simple xy that is x times y. This is some function of x and y, okay? Let's say this function of x and y is a function of two variables, obviously, x and y, with continuous first partial derivatives. So here we're doing partial derivatives, okay? Let me go, all right. P-A-R-T-I-A-L, partial derivatives. Now, we're not doing partial differential equations, but we are taking partial derivatives of this. And y'all all had Cal 3, so you've done partials, right? Okay. So, that's our assumption. These are continuous first partial derivatives. In some region R, and my string is called my thing, okay, of the xy plane, then recall from calculus that the differential dz, I don't know if you remember this or not, partial of f with respect to x dx plus partial of f with respect to y dy. Okay? Remember that? Usually we do differentials and don't really think much about them. This was, if these have continuous first partials, then this is true. Okay? Now, in the special case that this f of xy happens to be a constant, not a very interesting function, is it? Then this would have to be this partial of f with respect to x, I mean, this thing here, dz, would have to be 0. If z was a constant, then dz is 0. Okay? Why didn't we start there anyway? I mean, why are we messing with this? Okay? In other words, given a one-parameter family of functions, f of xy is equal to c, this thing right here, we can generate first-order differential equation by computing the differential of both sides of the equality. And so let's just give an example here. Okay, it feels like we're running in circles, but we're really not, I hope. Okay. X squared minus 5xy plus y cubed is equal to c. Okay, now that's a pretty legitimate problem, okay? It is a constant, but it's not a very simple constant, okay? It's got x, y dependency all over the place there. So that's your f of xy, okay? And it is a constant. So I was sort of making out that it's not very interesting. That could be pretty interesting, okay? Now, the partial of that, if that's your z, and it's a constant, then the derivative of this, dz, has got to be 0. Well, let's see what dz is. dz is, from what we just did before, the partial of x of f with respect to x dx plus the partial of y with respect to partial of f with respect to y dy, and that's got to equal 0. Okay? Well, what is the partial of f with respect to x? Can you do that? Partial of f with respect to x, if f is this function right here. Partial of that with respect to x. What is the partial of f with respect to x? 2x minus 5y. Perfect, perfect, perfect. Okay? Because when you're taking a partial of a function of multiple variables with respect to one of them, that's the only variable of interest. You count all the other variables as if they were constants. That's how you do partials. So this will just be 2x. That's pretty obvious. This is minus 5xy. X is the only variable there. You take a derivative of it. Count y as if it's a constant. So this would be like minus 5y times x. Well, that's your coefficient, minus 5y times x. So the derivative of that would be minus 5y. And then with y being a constant, the derivative of the constant is 0. So there's your partial with respect to x. What's your partial of f with respect to y? Now that you've got the rust out of there, what is it? A little louder. Negative 5x is a good start. Plus 3y squared. Perfect. There's your partial with respect to y. Okay, well, what do we have then? We have that 2x minus 5y dx, because the partial of this goes here, plus, I'm going to rearrange the order if that's okay, 3y squared minus 5x dy is equal to 0. Hey! There we have something that looks just like this. Some function, a coefficient function that has x's and y's in it times dx, plus some other coefficient function that has x's and y's in it times dy is equal to 0. Hey, this is a differential equation. Not one that I think we could do linear, separation of variables, or any other thing. No guarantee we could do it at all, but at least that's a differential equation that we may run into. So we need to know how to deal with it. Okay? Now, they left the minus 5y in front. I just don't like having that. Not every first order differential equation written in this form corresponds to a differential f of xy equals c. We just happen to make this happen, okay? So for our purposes, it's more important to turn the foregoing example around, namely if we're given a first order differential equation such as that one right there at the bottom, is there some way we can recognize that the differential equation there, that one, is a perfect differential of the function we started with, that one, the f of xy. Okay? That's the question. If there's some way to determine that, then the implicit solution of this would be that equation right there. So here is our definition. This sounds like we're running around in circles, but we really aren't. This is leading to something. Here's the definition, 2.4.1, for an exact equation. A differential equation, DE, no, I'm sorry. This is differential expression. Okay, so I probably should put, usually I use E for equations, so let me write it out. Okay, a differential expression, okay, m of xy dx plus n of xy dy is an exact differential, okay, exact differential in some region R of the xy plane, okay, if it corresponds to the differential of some function f of xy, okay, defined in R. Okay. A first order differential equation this time I'll use DE because that is differential equation of the form, and here's what we've had before and we're going to have it again several times, m of xy dx plus n of xy dy is equal to 0. Okay? It's said to be, I don't know why they don't just say is an exact differential equation. Okay? An exact differential equation if the expression on the left-hand side is an exact differential. If the left-hand side is an exact differential. Okay. Now, it almost seems like we're running in circles, but we're not. Okay? Here's an example that I hope we can do just by observation. X squared y cubed dx plus x cubed y squared dy is equal to 0. It says that's an exact equation, and it is because this is the exact differential, okay, of this. D by D, just D, leave it in differential form, okay? Okay. And it needs to be a product, remember, D of x cubed y cubed, okay? Not quite 1/3 of that. Because what is the differential that we did before, written like this, be partial of f with respect to x, 3x squared, right, times y cubed, dx, plus 3y squared x cubed dy equals 0. And you see the 3's and cancel out with 1/3. So yeah, that's pretty obviously an exact differential, okay, by the definition we had before. If you can tell this left-hand side is an exact differential. Now, most of the time, they're not going to be that easy to find. Guaranteed. Otherwise, we'd be through with it by now, okay? So, that's indeed the case. Okay. If we were, and actually, they put the 1/3 inside, which is fine. I took it on the outside. That's fine. Okay. Now, here's something to note. Here's your m, and it's multiplied by dx. So what if we did the partial of that m with respect to y? This is your m. So do the partial of that with, okay, let me write it in. X squared y cubed. Take the partial of that with respect to y. What does that give us? Second?
2x to the third. You said with respect to what?
Yeah. Partial of that with respect to y.
That's 3x.
3 x squared y squared. Okay. Now let's do the same type thing, only we'll take the partial of the second one, which is our x cubed y squared. Take the partial of that with respect to x. and see what we get.
3x squared.
3x squared y squared. Guess what? Same thing. Okay? That's going to be our test. If we have any big old hairy looking m of xy times a dx, some other big old complicated looking n of xy dy, and it's equal to 0, first thing we're going to do is take the partial of m with respect to y, the other variable, take the partial of n with respect to x, the other variable, and see if they're equal to each other. If they are, it's an exact differential. If they're not, it's not. Don't even try. Don't go any further. So that's going to be our test. Okay? So let me write down this theorem that supports that. All right, to erase. Do y'all need to take a break? I see somebody did. Anyone need to take a break? Okay. We'll keep going then. So, let m of xy, most of the time by now I do, but seems like I'm doing all right today. M of xy and n of xy be continuous. Okay. What would be some ways they wouldn't be? Okay. What are some ways to guarantee they are continuous? If they are, what kind of functions? Polynomials are always continuous, right? So if they're all polynomial forms, we can be pretty confident. If they're all sine and cosine forms, pretty confident, right? Exponential forms, yeah, pretty good. Tangent, nah, not continuous. Cotangent, yeah. None of the other trig functions are continuous except sine and cosine. Rational functions, they would be m of xy, but if anything in that denominator was 0, not continuous, okay? If anything evaluates to 0 in that denominator, not continuous at that point. So that's, you get a general idea. Most of the time if they're polynomials, maybe with sines or cosines, maybe with exponentials, be wary of anything else. Okay? So, but check and see. So if they're continuous and have continuous derivatives, okay, so again, when you take the derivative, continuous, let me put the modifiers in there you need. I was thinking them, but I didn't write them down. Continuous first partial derivatives. Okay, first partial derivatives in a rectangular region, okay, are defined by, this is the region R, A is less than or equal to X is less than or equal to B, C is less than or equal to Y is less than or equal to D. Right? No. Okay? They don't even include the equals. They are strictly inside, not on the border. Okay? Then a necessary and sufficient condition, NECES, and sufficient condition, okay, that m of xy dx plus n of xy dy is equal to 0. I'm sorry, you don't even need the equal 0. That to be an exact differential, okay, exact differential is this, that the partial of m with respect to y, the other variable, is equal to the partial of n with respect to x, its other variable. If that's the case, you can proceed and try to find the solution. If it's not the case, don't even try. Now, the top of page 66 is proof of that, of the necessity, okay? Which is again one of these cases that you go round and around and change this and that, and it actually almost makes you dizzy, okay? But it works. I mean, you can go through that and see that the proof is indeed there. The sufficiency part, that's the necessary part. The sufficient part of that theorem consists of showing there exists a function for which partial of alpha with respect to x is equal to m of xy, and partial of alpha with respect to y is n of xy whenever that equation holds. And the construction of the function f actually reflects the basic procedure in providing the exact differential. So in other words, how we're going to do that basically fulfills the definition by how we do it. And again, very circular seeming. So here's the method of solution. And again, don't try to memorize steps. Follow the pattern, okay? Given an equation in differential form, okay, so I'm going to go back and start over. It's going to say a lot of this other stuff, but let's get it together. Given an equation in differential form, you'll see it like this: m of xy dx plus n of xy dy is equal to 0. Okay? Always going to be equal to 0. Okay? Now, determine whether our condition holds. In other words, the first thing you do, you check to see if partial of m with respect to what? Anybody with me? What partial do you take to check to see if it's doable? No, the other one. This is dx, so do it with respect to the other. Check and see what that is. See also what this is. What's the other partial you check out? N with respect to x. Okay? Do those two. See if they're equal. If they're not equal, forget it. It won't work. Okay? But if they are equal, then proceed. Okay? Don't try it if those, but always check that first. Okay? Now, if it is equal, if that condition is met, then here's what we're going to do. Remember, we need to see if there's some function f that is a perfect derivative. You know, okay? So, we don't know what the f is, but let's just say the partial of that f with respect to x. Okay? We know that has to be m of xy, right? That's where we started. That there is some function out there, f of xy, that when you take the partial of it with respect to x, plus the partial of it at dx, plus the partial of it dy, it's going to be 0. So this is the first condition to be met. It has to be that. Okay? Now, what we're going to do next, hopefully you'll find it's all right to do. Okay? We're going to integrate this. In other words, multiply this by dx. Okay? And kind of let that take away the partial. I mean, it doesn't look like that's the same, and it really kind of isn't, but do it, it works. Okay? And integrate this. but only with respect to x. So again, you're counting your y's as if they're constants, okay? And do that integral, okay? So then we're going, this is just going to give you f of xy is equal to some value, integral of m of xy dx. Now, when you take an integral, you may wind up with a constant, right? Because this is an indefinite integral. So you expect to have a constant, right? But because this is a function of x and y, and you're only taking the integral with respect to x, that constant could also be some function of y. So they're going to throw in a g of y here. Because we're holding y's constant here when you're doing the integrals, so it could wind up with an extra function of y, because you're not integrating with respect to that. Okay? That's now your constant function of integration, just not constant of integration. Now, all right, we just integrated this. Now we're going to take a derivative of it, okay? But this time we're taking the partial with respect to y. Take the partial of this f with respect to y, not x. If you did it with x, you just undo everything you just did. Do it with respect to y, okay? Now, remember, this is some integrable function. So you can take the, you know what it is. So this is, but we just don't know. It's just an mxy now. So take the partial of this with respect to y, of this integrable function, m of xy dx, okay? And then when you take the partial with respect to y, it's not a partial anymore, because that's only a function. So this is g prime of y. That is your derivative of g. Not partial derivative, derivative, because there's no x dependence in that g. Okay? Now, here's what we got to do. Because the partial of f with respect to x was m, the partial of f with respect to y had better be n of xy. Okay? So, remember, this is some function you can integrate. You integrate that, take the derivative of that, partial of this thing with respect to y, and the partial with respect to derivative with respect to g of y, and then you have to set those equal to n. Okay? So that allows you to adjust through g and this thing so that that equals n of xy. And that's how you get your n. If you can do that, then, okay, that gets you that far, okay? Now, this enables you to solve for g prime. See, we just introduced g, we don't know what it is, but that g prime of y is equal to n of xy, and this is way more complicated than it is in real life, minus the partial of, with respect to y, of the integral of m of xy dx. Okay, again, you've already evaluated that. You don't have to haul it around, but this is what your g prime is, and then what you do here is integrate that. Okay? Because the g prime is dg dy. Okay, remember that was a function of y alone. So, so you take a derivative of that, which is a partial of this, and the derivative of that. And again, it really looks complicated. Truly, it looks complicated, but it really isn't that bad in real life. Okay? And whatever you get here when you integrate this, in other words, do dg is equal to all this stuff dy. Integrate that, you get g. Integrate all this with respect to y, not messing with the x's any. And what you get there is a g. Plug that g back in here, and you wind up with your f of xy, which is what you were looking for. That's your solution. Okay? It says never memorize these equations. Okay? Oh, I forgot. When you plug that back in, sorry, I jumped ahead a little too fast. No, I'm sorry. No. I'm sorry, I looked down too far on the page. That gives you your f of xy. It says here, second, we could have just as easily, it says some observations are in order. First, it's important to realize that the expression n of xy minus the partial of that is independent of x. That's this step right here, this one up here. This one right here has no x dependence on it. Yeah, you see the x is in there, but it's not depending on that. Okay? Secondly, we could just as well have started this by, instead of going partial of f with respect to x is m, you could have done the partial of f with respect to y is n. It doesn't matter. In fact, do whichever one makes it easier. Now that's, I admit, a lot of blah, blah, blah. Okay? Let's actually do one. And I think you'll see it turns out to be much, well, at least a little simpler than what it seems like. Okay? Here's what we got. Let me fix my pen. Okay. Remember, the goal is to find the f of xy. That is your solution. Okay? So here's what we got. 2xy dx plus x squared minus 1 dy is equal to 0. There is a differential equation. Now, it's an unusual form, not one we're used to doing. I'm almost guaranteeing you, I don't know, this looks like it might be separable, but that's okay. We still want to solve it this way, okay? So it should come out fairly simple. I think it would be separable if we tried, and we can go back and do that in a minute if you want to. But let's see if we can do it this way. What's the first thing, the condition that has to be met if we're going to solve it as an exact? We got to determine, is it exact? So what's the condition we go for? What's our check? What's the criteria that must be met? I'll get it started. The partial of, m, the first one. 2xy, partial with respect to what? Y. Is that equal to what partial? Yeah. X squared minus 1 with respect to x. There's the question. If it is, we can proceed. If it's not, stop right there, go to the next problem. What is the partial of that first one with respect to y? 2x. What's the partial of this with respect to x? 2x. Ding, ding, ding. We can proceed. Those partials are the same. That means this is an exact differential equation, so let's go from there. All right? Now, What we do next is, let's say, because it's exact, we know there is some f. There is some f of xy such that, and what's one condition that has to be true? Partial of that f with respect to x has got to be this 2xy. Do you agree? It's got to be. It's got to be. If there is a solution there, the partial of that solution has got to be your m. It's got to be that 2xy. Right? That's how we set it up to begin with. Partial of alpha with respect to x dx with partial of alpha with respect to y dy is equal to 0. Okay, if that alpha is a constant. Okay, so sure enough, we expect that it's got to be true. Now, what's the next step? Kind of a stretch here, but we do partial of f is equal to 2xy times dx. Okay, now that's not quite kosher, it seems like, but it works here. Okay, in other words, write it in differential form. And now integrate with respect to x, not with respect to x and y, just with x. So this is still going to give us a f of xy. And what is the integral of that with respect to x?
X squared.
That's part of it. X squared y. But our constant of integration is now a function of integration because we're integrating with respect to x. We haven't taken into account a y, so it can be some other function, g of y, right? That's our constant of integration is now a function of integration with respect to y. Okay? Next thing we got to do. Here we started out taking the partial of our f with respect to x, knowing that had to be our m. Now that we know kind of what our f is, we need to take the partial of that f with respect to y. Okay? And what is that? That's your f, so what is it? Partial of that with respect to y. X squared nope, g prime. Because you take it with respect to y, that's the derivative of g with respect to y. G prime. Okay? Now, we want that, and you're right, in a sense, we want that to be our n. So therefore, if n is x squared minus 1, what is g prime got to be? He's 1, okay? So dg is equal to 1 dy, right? Let's integrate that one. And what do you get? G is a function of y alone, remember? What would that be? Y. Why not? Okay? So let's plug that back in here, and your f of xy is equal to x squared y plus y. There we have it. Yes? Second?
Where did you get DG from?
Say one more time. Where did I get what from?
DG. Or is that dy?
Oh, this right here?
Yeah.
Okay, that's g of y. I was just reminding you, this g is a function of y alone. That's all. That's why I put of y in there, because it's only a function of y alone. So there is no x in it. Can be no x in it. Okay, there could be numbers, but it can't have any x. Only y's. And really, what we've got, have we taken into account a constant? Could we have a constant with it? I don't believe so. I think that's all we have to do. Let me just see, make sure I'm not leaving something out. Okay. So, now here's where the constant comes into play. That f of xy, remember from the very, very, very beginning, we said that function had to be a constant. That's why the derivative is 0, right? So now that we have this, we put at equals c. There's our constant of integration. Okay? Now, in this case, it happens to be we can solve that as an explicit function of y, not just implicit, but explicit. What would that be? What would you do to solve that for y? Any guesses? This equation right here, solve for y. When I say solve for y, that means sort of isolate the y. Get the y completely by itself. Think of a naked y, nothing else messing with it, right? Just y. Okay? So what would be the first thing you'd have to do to isolate the y? Factor it out of both terms. That would be y times, that's not what you said, was it? Okay, I know. But I'll try to encourage you that way. Okay? So, okay. Y times x squared plus 1 is equal to c. And guess what we can do now? Isolate the y, divide both sides by x squared plus 1. And that gives you y is equal to c over x squared plus 1. Whoa! All right. Now, if you really want to run in circles, you could take that and I wouldn't. If I was going to run in circles, I would just start here, do the partial of this with respect to x dx, see if you get that. Partial of this with respect to y dy, see if you get that, and sure enough you get it. But there's your y is equal. There's your solution as an explicit function of y alone. Okay? And that's where you could have, at the very beginning, excuse me, I think done separation of variables and gotten the same thing. Okay? But they wanted to show the method with something that's relatively easy. Okay? Now, the next question, and I may have messed something up here. It seems like I did. Yeah, I put a plus here, and that is actually a minus, isn't it? Where did I do that? That should be a x minus 1. And I can't see. I know we're, oh, yuck, we are out of time. That's a minus 1. And I see that it should be a minus 1, but I don't know where I got the plus from. Right there I have n minus 1. I think I just wrote it wrong. This has to be a minus. Okay. But anyway, what I was going to say, this is not good for every interval from minus infinity to infinity. Obviously, this answer is not valid x equals +1 or -1. So your intervals of integration, intervals of everything, has to be less than -1, between -1 and +1, or greater than +1. You cannot include an interval that crosses either of those asymptotes. So that's the only thing to do there. I just, for the life of me, where does it fit? I think it was just as simple as saying G prime is equal to G is equal to -1. I said it was +1. Sorry, but we don't have time to go back and find it. All right, we got a little ways in this section. Let's see if there's any you can do for homework exercises. I say you could do any of the odds 1 through 3. You could probably do 5. You might even be able to do 7. I would stop there. Go no further. You can if you want to, but we'll next time solve one that has the other in it. Good deal. Sorry, messed up that right at the very end, but have a good weekend, and of course, working on differential equations will make it good, right? Good deal.